All right, here we are back for a final lecture for the energy unit. Okay, so this is going to capture the last part of chapter 13, so the final pages after the solar energy piece, the active, passive, indirect, direct solar energy, all those things that encompasses. So we're going to be focusing primarily on non-solar renewable energy sources. Okay. The first one we'll look at is geothermal, which is widely used in Iceland, by the way, just because of the lots of volcanic activity they have there. There's parts of the U.S. where this is being used as well. You can imagine a place like Yellowstone, where there's lots of geothermal energy at the surface, would be a great place to use geothermal energy. Okay, but Iceland's probably, as far as countries go, the widest user of geothermal energy. And essentially what that entails is taking the heat energy from the interior of the Earth, which is generated through, really a lot of that's radioactive decay, generating heat. So it's actually, you could almost consider it a form of nuclear energy. We're just taking the heat that's produced on the interior of the Earth and using that heat to produce energy for us. In some cases, that means producing electricity, as shown in this diagram to the left here, where they're taking the hot water to produce steam. Steam spins a turbine, so we have the steam turbine idea, but using heat from the interior of the Earth as opposed to combustion and so on. Or we could just use that heat to heat buildings and heat spaces. Either way is considered geothermal energy. Okay? And so, stupid bell, every time, that darn bell. Anyways, we have geothermal energy with a steam turbine or geothermal energy for space heating. One of the ways it's used exclusively for space heating is through this idea of what they call a geothermal heat pump. And in this case, they're not using like intense heat, so this doesn't have to be done in an area that has geysers or hot springs nearby. This could be done in an area that just, anywhere, essentially. And what they do is, because the temperature of the ground, you get below that frost line, and in different areas, it's a different depth, of course, the temperature remains relatively constant, and they can use that constant temperature to cool us off in the summertime, but also to heat us up in the wintertime. They essentially just reverse the direction that heat's going. So it's kind of an interesting little exchange there. So because it stays relatively cool compared to summer temperatures, they can pump air underground and use it as a heat exchanger, and the air that comes back in the pipes is a little bit cooler. Much cooler than probably the ambient temperature. And likewise, in the wintertime, they can use the fact that it stays warmer than the ambient temperature to aid in the heating of a building. Okay, the installation is expensive, but once it's installed and going, it's all you're paying for is essentially a fan. It's pretty simple from there on out. So there's a few buildings here in Walla Walla that make use of this, but again, you'd have to fork over the cash because, as you can imagine, installing these pipes and stuff underground in the construction could be a bit expensive. All right, so other renewables. So we've got potential to use tidal energy. So in coastal areas, particularly in narrow inlets, we could use the fact that water is moving throughout the day as a result to gravitational pull of the moon and sun. All right, and that moving water could potentially be used to spin a turbine, and that turbine, of course, could spin a generator. Okay, narrow bays, like I was mentioning earlier, have greater variation in tides, and the water tends to move a little faster. In fact, if any of you have ever been to that Malibu camp up in Canada, that's part of Young Life, that inlet there, it looks like a river is moving. That's actually just from tidal motion. So they could produce actually a lot of energy in that little inlet right there. So you could put a dam across the bay, although not so environmentally friendly, but some sort of turbine underwater that spins could create electricity for us. Of course, this has to be done in coastal areas. Probably the next most widely available option for us, aside from wind and solar, is hydrogen. Hydrogen is an interesting fuel source. First of all, it's super abundant. It's everywhere. It's the most abundant element in the universe. The way it is right now, though, most of the hydrogen on Earth is locked up in water. So, but what's both promising and problematic for hydrogen is it's really, really energy dense. And we saw that in that fuel viability matrix we worked on earlier. But, per unit weight, hydrogen is head and shoulders above any other combustible form of energy. Super, super energy dense. That also makes it problematic because it's so volatile that it can tend to have explosions, which is not necessarily a desirable quality. And so it's problematic to use for combustion for that reason. It's also locked up in water on Earth, and because it's locked up in water, we do have to input some energy to extract the hydrogen. So typically we would do a process of electrolysis, which is essentially running an electric current through water that has electrolyte in it, and in doing so you can separate the hydrogen from the oxygen and extract the hydrogen that way. Which would mean, because of thermodynamics, we'd have to put more energy into the process than we actually get out of it. So we would have to then probably get the energy to separate the hydrogen from the oxygen using some sort of like solar energy or something like that that's renewable. If we used fossil fuels for that purpose, then it would be absolutely pointless. Okay? So hydrogen shows some promise. It's just difficult to get, and it's dangerous to store and use because it's so volatile. And it's problematic because we need to then condense it. It is such a light element that, per unit weight, it's really energy dense, but the volume of it needs to be condensed so much to get much energy stored, that creates problems. Okay? And so our most likely use of hydrogen fuel was probably for fuel cells. So rather than combusting the hydrogen, we use it in a fuel cell, which generates an electric current as opposed to combustion. Okay, the trouble with this is it's expensive. Right, part of the reason it's so expensive is it involves things like platinum, sort of expensive metal. And the use of these fuel cells, we're not talking being able to power like an 18-wheeler, right? We're talking small vehicles. So looking at the little personal transportation things like this little motorcycle type device here, with just to kind of scoot you around town. Probably not going to be used on a large scale for trains and things like that. It's too hard to put enough hydrogen in one spot because you have to compress it so much. So small electrical components, batteries for laptops, stuff like that, could probably run off fuel cell technology. All right. Now, energy intensity. It's a concept in terms, basically kind of rates the efficiency of turning energy into GDP or vice versa. And so a low energy intensity kind of refers to the efficiency of an economy. Okay? So for each, dollar produced, how much energy is required. And so companies like Japan and Germany have a relatively low energy intensity, which means requiring less energy to produce dollars for their economy. And countries like the United States, you'll notice that we've had significant decreases in that energy intensity, but we're still quite a bit higher than places like Germany and Japan. All right? So when it comes, all these renewable technologies, all the solar, the wind, etc., all of them are great. They're great replacements. The technology is getting better. But the single most important thing we can do to help us with energy transformation is efficiency and conservation, which really comes down to just needing less energy to carry on our daily activities. And so that comes from energy efficient houses, so that we're using less electricity for things like lighting, less electricity, natural gas, etc. for heating and cooling. And that just comes down to insulation. And there's best practices, there's LEED standards, appliances that require less energy, automobiles that are more fuel efficient, aircraft that requires less fuel. If we can tackle a big part of our energy transition just purely through efficiency. And as much as 40 to 50% of our energy could be better utilized. And that makes it so much easier to meet our needs with things like hydro and nuclear, with things like solar and battery backups and so on. All right. One of the things we can do in terms of efficiency is taking waste heat and using it in a process that we call cogeneration, which basically you take heat from any sort of industrial process, even from power plants. So a lot of that heat that's generated in those steps is just radiated out into the environment. We could use that heat for a second purpose, for heating buildings and so on. Okay, so this diagram kind of shows the basic idea of cogeneration. Right? So we have waste heat from whatever process. It doesn't even have to necessarily be electricity production. We use that waste heat for the purpose of heating buildings or to recycle that heat so we don't have to do as much heating for the initial process. And that's that idea. Another way to be more efficient and conserve energy. All right. Some cool findings, and they don't really entirely understand why, is when some energy efficient appliances, in particular lighting, are implemented in buildings, they had some unexpected benefits. And the best guess probably for why this occurs is a lot of the energy efficient lighting is also made to try to mimic natural light. And in doing so, they think that has sort of a subconscious mood alteration. Because that natural light is mimicked, people tend to be subconsciously in slightly better moods, and productivity and absenteeism tended to go down. Really interesting byproduct of energy efficient lighting. I don't know. They don't entirely know why, but that's probably the best guess as to why. So energy saving at home. This goes just, these are kind of habits, right? Of course, I mean, you all probably learned at some point to turn off appliances where they're not in use. If you leave a room, turn the lights off. Those are habitual things. Thermostats in your house. During the wintertime, if you set it to 68, that's a little colder maybe than your comfort level, but that allows for things like your appliances and body heat to heat things up. You know, if you're sitting on the couch watching TV or doing your homework, you don't necessarily have to wear shorts and a t-shirt. Wear a sweater during the wintertime. Likewise, in the summer, set your thermostat to 78. Okay? Now, that might not be the most comfortable temperature, but it is certainly tolerable. 78 degrees is what we set ours to. That's pretty darn comfortable for most of the day. Okay? But just want to reiterate, a lot of our energy transition to making a sustainable energy future, so much of it isn't technology based. It's just behavior and efficiency and conservation. If we can get that part down, it makes the transition to renewable so much easier. The saying is, and I didn't invent this, so you can't make fun of me, Ed, but the saying is, you got to have your conservation vegetables before you have your solar dessert. Which means you got to do those conservation measures before you even think about putting solar panels on your roof or personal wind turbines. All right? That concludes the energy lecture unit.